Dear students, today we are going to do second law of thermodynamics and we'll try to cover up the entire chapter in the least possible amount of time without skipping any concepts. So these are the concepts that we'll cover in the second law of thermodynamics. Why is the second law required? What is the Kelvin-Planck statement? What are heat engines? What is the Clausius statement and refrigerator heat pump? What is Clausius inequality and how it gives birth to the concept of entropy? What is entropy generation? How do we calculate the change in entropy? What are TDS equation and how to draw a TS diagram? You see, this lecture is full of concepts. I hope you will enjoy it. So the first question is that why do we need the second law of thermodynamics? The second law of thermodynamics is required because the first law is not sufficient enough. The first law only tells that energy can neither be created nor be destroyed, but it fails to explain why certain processes takes place only in one direction. The reverse is not simply naturally permitted. So the second law gives us two things. First, directionality means in which direction a certain process is feasible. And secondly, we will see it also tells us about the quality of energy. Now, the first law only tells about the quantity, that it remains conserved. The overall quantity of energy will remain same. The second law goes a step further and it tells us that not all energy, for example, heat and work, are not the same in terms of quality. You'll see later on, you'll understand that work is of higher quality and heat is of lower quality. So let us try to understand this with an example, right? The directionality. Now, if you keep a hot cup of coffee, which is say at 50 degrees centigrade in a room, which is say at 25 degrees centigrade, now heat will flow from the coffee to the room and eventually the coffee will cool down. But the opposite never takes place naturally. Yes, you can put it in the refrigerator and cool it, or you can put it in the microwave and heat it, but that is not a natural process. Naturally, the opposite is not possible. Similarly, if you take it is much more uh, understandable, right, using a resistor. Now, if a current flows through a resistor, it generates some amount of heat, right, which can be given as I square R. Now, the opposite is not true. If you heat the resistor, right, it will not generate current. So why is it so that some processes occurs only in one direction and not the reverse is not possible? The second law of thermodynamics answers these questions. Now, what is second law of thermodynamics? Now, the second law of thermodynamics is basically given by two statements. There are two statements of second law of thermodynamics. They are the Kelvin-Planck statement, and one is the Clausius statement. So we'll understand both of these statements and what exactly they mean in short time. But before that, we have to understand what are thermal energy reservoirs. Now, thermal energy reservoirs are some kind of a hypothetical body. It is also real, we'll see that, right? So, which can supply or absorb infinite amount of heat without changing its temperature. Huh? How? I'll give you an example, right? Now, thermal energy reservoirs can be of two types, source and sink. If the reservoir is supplying energy, it is known as source. If it is absorbing energy, it is known as sink. Now, let us take the example of sun. Now, sun for so many years, right, billions of years, it has been supplying energy to us at the same constant temperature, isn't it? So it can be assumed to be a thermal energy reservoir, right? It is a source. And it is true. If you are taking making solar cells, this is true. This is the source. Sun is the source of energy. At the same time, we can consider the atmosphere to be a sink, thermal energy reservoir. For example, all our engines, be it our thermal power plants or jet engines, everything is rejecting heat into the atmosphere. But temperature of the atmosphere is not rising. The atmosphere keeps on absorbing the heat, but temperature is not rising. Now, you might say, so what about global warming? Now, see, the global warming is a phenomenon which is because of many different factors, not just because of this heat rejection, and it is not taking place immediately. It is taking so many years for the atmosphere to get heated, that too by 1 to 2 degrees, right? So that is a different aspect altogether, right? So I hope you have understood that from source we will get energy, right? And sink is where we dump energy. Now, let us try to figure out what does the Kelvin-Planck statement say. Now, Kelvin-Planck statement says that it is impossible for any device operating on a cycle to receive heat from a single reservoir and produce net amount of work. Now, slowly you will understand that, see, what is the role of thermodynamics? What is the main concept behind thermodynamics? Thermodynamics is a study of energy. Even more precisely, if I say, it is study of the science, how energy can be converted into power, right? Work. So we'll see in short while that we can use a thermodynamic cycle to convert what? Heat energy into work energy. Right? Now, what the Kelvin-Planck statement says is that it is not possible for any heat engine, we'll understand heat engine in a short time, for any heat engine to operate in a cycle and simply convert heat into work without rejecting any heat. Achha? Can you explain it once more? Yes, it simply says that every engine, right, must have a sink, and every engine must reject some heat. Okay. So this is what a heat engine is like. Let us try to understand what is a heat engine. Right? So heat engine are devices that convert heat into work. This is what is the main concept behind studying of thermodynamics. We want to create systems, engineering systems, right? Devices that can convert heat into work, isn't it? And heat engine is such a device. All our jet engines, thermal power plants, right, everything which is producing work, right, are form of an engine, be the IC engine, right? We are going to see. And an engine, it operates in a cycle. Any engine, it has to operate in a cycle. It will contain minimum of 3 processes, and some engine also goes up to 5 processes, right? But generally you'll see there are 4 processes. Let us try to see how does a heat engine function. Let us have a quick overview so that we can understand the concept of heat engine properly. Now, there is a high temperature source. Basically, if we take a thermal power plant, let me say how the thermal power plant uh, produces work. So the furnace where you are burning the coal or the gas is the furnace, right? Which becomes the thermal energy reservoir, the source, which is supplying energy at the constant temperature. Now we have a boiler where there is water. The water absorbs the heat and converts into steam. Now the steam is passed through a turbine, and the turbine blade rotates, right? The steam expands and the turbine blade rotates, and it produces some amount of work. It produces some amount of work. After that, the steam is passed through a condenser. The condensation process takes place. So the steam, which is in vapor state, it is converted into liquid, and some amount of heat is rejected to the sink, which is generally the atmosphere or might be a lake or something like that. Okay? And then the steam is sent to a pump, and the pump again increases the pressure of not the steam, now it is liquid, it is water is pumped into the boiler once again. So you see there are four processes here: one process in the boiler, one process in the turbine, one process in the condenser, and one process in the pump. And this is a cycle, and you see in this cycle what is happening, we are getting a net work output. Now you can say we are also using some energy to run the pump. Yes, that is mainly done through the turbine itself. Some amount of work output of the turbine is used to run the pump, because the um, energy, the work output produced is much larger than the work input required by the pump. Now you see, for a heat engine, if it is accepting some energy from a high temperature source, it is also rejecting some energy to a low temperature sink. And this is what Kelvin-Planck statement says: you have to reject some heat. It is not possible to have an engine without rejecting heat. So what is the heat engine doing? So heat engine is actually running in a cycle, right? This cycle keeps on continuing. So it absorbs heat from high temperature source, right? It produces some work and then rejects the rest of the heat to the low temperature sink. So this is what a heat engine does. Now let us try to apply first law of thermodynamics to a heat engine. So what does first law of thermodynamics says, right? For a cycle, we have seen that for a cyclic processes, right? Sorry, first, my bad, F-I-R-S-T, F-I, first law. So what does the first law says for a cycle? For a cycle, we have seen total heat supplied is equal to the total net work done. Right? So net work done is basically, what is net work done? This is turbine work minus pump work. Right? So what is the net heat supplied? Can I say this is Q in minus Q out? It is equal to work net. Right? So Q in also sometimes it is written as QH because this is the heat input from the high temperature source minus QL. This is heat rejected to the low temperature sink is equal to work net. Right? This is what the first law of thermodynamics says. Right? And yes, we'll go into detail. Right? We'll go into detail. We'll find out how much heat is required. Right? Now, what does efficiency, if you want to calculate the efficiency of a heat engine, efficiency can be given as the work net divided by how much heat has been supplied, right? So this is basically, it can be written as work net divided by how much heat has been supplied, that is QL, oh sorry, QH, the higher heat. And work net can be written as QH minus QL divided by QH, because we have seen work net is nothing else but QH minus QL. So in other words, efficiency of a heat engine can also be written as 1 minus QL, total amount of heat rejected divided by total amount of heat absorbed. Now, one way of looking at the second law of thermodynamics is also that if QL is equal to 0, what it means? That the efficiency of the heat engine becomes 100%, which is not possible. This is also something how you can interpret, right? Efficiency of a heat engine can never be equal to 100%, let alone more than 100%. It has always to be less than 100%. Later on, we are going to see what is Carnot engine, and it will tell us what is the maximum efficiency of a heat engine possible. So having understood what is the heat engine and how to calculate its efficiency, let us move on to the second statement of second law of thermodynamics, that is the Clausius statement. Now the Clausius statement and the Kelvin-Planck statement, they look different. They're written in different ways, but ultimately we'll see later on, both of them are saying the same thing, right? They are giving us the directionality of certain processes, in which direction a process is feasible and in which direction the process are not feasible. Now, what does Clausius say? The Clausius says that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a low temperature body to a high temperature body. In short, if you want to simplify this definition, we can say that heat cannot move from cold body to hot body without any work. So we will require some work. We will have to give it some work if you want to move heat from low body to higher body. Now, a device which does. Now let us try to understand what are refrigerators and heat pumps. Now these devices, it transfers heat from a low temperature medium to a high temperature medium. So, for example, what is the basic difference between, you'll be asking, what is the basic difference between a refrigerator and a heat pump? Now, in the outer world, both of them will be both of them will look same, right? But if you see about a desired effect, what is the desired effect? Desired effect. Desired effect is for the refrigerator, the desired what we want that is colder space needs to be cooled. For example, the AC. AC is also kind of a refrigerator, right? So we want to cool the room, right? So heat is being extracted from the room and it is supplied to the high temperature surrounding. So the desired effect for a refrigerator is going to be QL. That is how much heat is being removed from the uh, colder space. Heat pump is exactly the opposite. The desired effect is heating something. If you want to keep a room hot, then we can simply reverse the AC, right? And we can use it as a heat pump where it will heat up the room. So what it is going to do, it is going to take up heat from the atmosphere and then pump into the room, which is already at a higher temperature. So desired effect for a heat pump is going to be QL. So this is the basic difference between heat pump and refrigerator, but both of them will be working in a cycle, right? And we will require to put in some amount of work. Will require to put in some amount of work for the refrigerator or heat pump to work, right? And it is also going to operate in a cycle, right? It is also going to operate in a cycle. Now, for refrigerators and heat pump, we don't define efficiency. We don't define efficiency. Instead, what we define is coefficient of performance. Coefficient of performance. In short, we call it COP. Sorry. In short, we call it COP. So what is this coefficient of performance? Now, coefficient of performance, COP, is defined as desired effect by work input. Okay. Now, first, let us try to calculate what is the work input from first law. Okay. We all know what is first law. What is first law? First law says for a cycle, we can say the net heat transfer is equal to net work transfer. So heat transfer here is, what is the net heat transfer? I can say again QH minus QL, right? This is the net heat transfer. This should be is equal to the work input, right? Now, if I want to talk about COP, right? So if I want to write COP of the refrigerator, if you remember refrigerator, we want to keep the space cool. So QL becomes the desired effect. So it is going to be QL divided by work input, right? Which can be also written as QL divided by work input can be written as QH minus QL. Now, if you want to find out the COP of a heat pump, how to write the COP of a heat pump? Now, for heat pump, the desired effect is heating up a space. So QH is the desired effect. This is what we want, QH, right? Divided by work input. So this becomes QH divided by QH minus QH. So this is the COP of a refrigerator and COP of a heat pump. And we will see this once again when we do after doing Carnot cycle, because in Carnot cycle you will say you'll see that the ratio QL by QH, right? It can be represented in forms of temperature also if the processes are reversible, but we'll take some time to understand what are reversible processes and what is Carnot cycle before that, and then we can actually revisit these concepts of heat engine, refrigerator, and heat pump. Having said that, let us now move on to a machine which will violate the second law. If a machine is violating the second law of thermodynamics, it is known as perpetual motion machine of the second kind, PMM2. Basically, you can see this is a diagram, right? Let me say this is the thermal power plant, you can see there is no condenser here. So there is no heat energy rejected, right? So it is violating what? It is violating the Kelvin-Planck statement, which says that for a engine to produce work, for an engine which runs in a cycle to produce work, it must reject some amount of heat, right? So why it is important? Because if any scientist, any engineer proposes a engine which violates the second law of thermodynamics, better not to pursue them because they are not feasible. Having understood this, now the question arises how to maximize the efficiency or COP of engineering devices. Now you'll be asking, so why? Why do we need to maximize the efficiency? Entire thermodynamics is the study of how to convert energy into work, isn't it? And finally, we are able to understand that by operating in a cycle, accepting heat from a higher temperature source and rejecting heat to a lower temperature source, in a heat engine can actually produce some work. And if vice versa, we can also cool down a space like the AC or the refrigerator or a heated room using the heat pump. But now the most important question that comes to mind that okay, we can create those kind of engines and refrigerators and heat pump, but how to maximize the efficiency of the heat engines? Means how can we produce an engine which produces maximum amount of work? Or if we talk about refrigerators, how can we increase the COP of a refrigerator? It simply means building a refrigerator or an AC which consumes the least amount of work, right? Economical, basically. So scientists started researching, and they came up with the conclusion that for you to achieve this, you have to make sure that the processes are reversible in nature. Reversible cycle. A reversible cycle is a cycle which all the processes are can be reversed. Reversible cycle? What do you mean by reversible cycle? How to create a reversible cycle? Well, we'll understand what is the meaning of a reversible cycle in short while, right? So basically, you can create a reversible cycle by avoiding all the irreversibilities. Avoid all irreversibility. So what do you mean by irreversibilities? Now, irreversibilities means things which cannot be reversed in simple idea, right? Reversible means things which can be reversed without causing any problem. Everything can be reversed. Irreversibilities means things which cannot be reversed. So what are the things that can not be reversed? What are these irreversibilities you are asking us to avoid? This is the question that arose. The answer was that these are the main causes of irreversibility which we want to avoid. And if we are able to avoid them, we will be able to produce engines which are the most efficient. And what are these irreversibilities? Friction. For example, let us take the first thing, friction, right? Once, because of friction, what happens is that the energy gets dissipated because of the heat, mostly. Right? The surface gets heated up and energy gets dissipated. Right? And that is a waste, complete waste. That dissipated heat, that the energy goes complete waste, and it cannot be reversed once uh, say kinetic energy gets depleted. Once kinetic energy gets depleted because uh, of friction, right, into heat, now it cannot be reversed. Now you cannot just heat up and you convert it into kinetic energy. So that is the role of friction, right? Similarly, if you do fast compression and expansion, right, that is if a process is non-quasi-static, it also causes irreversibility. If you add heat through a finite temperature difference, means from a hot body to cold body, right? Finite. The temperature difference is finite. Even if the delta T is equal to 1 degree centigrade, right? It is going to cause some irreversibility. We're going to see this all these things, right? Unrestrained expansion simply means free expansion. If you're doing free expansion, right, it simply cannot be reversed. Right? Mixing of fluid, electrical resistance, chemical reactions, inelastic deformations of solid. So these are all irreversibilities. We need to avoid them. The first four are related to thermodynamics. The first four are related to thermodynamics. You might be understanding elastic deformations of solids also. If we stretch a solid beyond its elastic limit, what happens is that it cannot regain, it cannot come back to its original position. And that is a permanent damage, right? That is something which is irreversible. Right? So what the scientist said, you need to avoid these irreversibilities. By avoiding these irreversibilities, you'll be able to produce a reversible cycle. And if you're able to produce a reversible cycle, then you will get the maximum work output. Or in case of refrigerators, heat pumps, they will consume the minimum work. Now the question arises, now how do we do this? Right? Avoiding friction, or you want to transfer heat without maintaining a temperature difference, right? You want to do a non-quasi-static process, infinitely slow process. Now how are these things possible? Yes, these are perfect. These are the ideal things, right? We might not be able to achieve them, but we should try to move towards them. We should try to achieve them as much as possible. Right? It might be very impossible for us to do it, but we should try to do it. Then the question asks, okay, if we are not able to completely eradicate, completely stop these irreversibilities, how do we minimize them? How can we minimize these irreversibilities? So the scientists kept on researching, scientists kept on researching, and the scientist named Clausius came up with the answer. The scientist named with Clausius, he came up with the answer, and he said, he gave an equation which came to be known as Clausius inequality. And through this equation, he tried to explain that how can we actually build reversible cycles. So what is the concept? What is the core first principle behind building a reversible cycle? Right? So he said he gave a inequality. Why it is inequality? He said the cyclic integral. He said cyclic integral of dq by t for a cycle should always be smaller than equal to 0 for a cycle. Now the others, they were unable to understand. What do you mean by this? That cyclic integral of dq by t is always smaller than equal to 0. What do you want to say through this? Then he further went on to explain that if the cyclic integral of dq by t, if it is equal to 0, then the cycle is reversible. Reversible cycle. If the cyclic integral of dq by t is smaller than 0, well, the cycle is irreversible, but it is still possible. It is still possible that a cycle takes place and it produces work, or say consumes works, and heats up a means you can basically manufacture a heat pump, refrigerator, or heat engine using that kind of cycle. But if cyclic integral of dq by t is greater than 0, what it means that that cycle is not possible, impossible cycle. So simply said, if for a cycle, if it is coming out to be greater than zero, better you not focus on that cycle. You have to improve something. That cycle is not possible. Now the scientists said, even now we are unable to understand. So what is this term dq by t? Okay, I understood that in a cyclic integral of dq by t is equal to zero. If you can do this, right, we can actually produce a reversible cycle, right? Or at least we have to make it as close to zero as possible, right, to make it a irreversible but possible cycle. But what is this term dq by t? Then Clausius went back and he started researching more and more and more and more. Clausius went on and he did the research and research and research, and he came up with the concept of entropy. And then he started explaining. He said that for a cycle, the cyclic integral of dq by t should be equal to zero. Now, if you want to build a reversible cycle, right? So what does this mean? Let us try to understand, right? Let us first to understand this, let us draw a cycle. Let me say the system initially was at point 1, then it moves from point 1 to point 2, the first process, then point 2 to point 3, the second process, point 3 to point 4, the fourth process, and then again finally to point 1. Now, what does cyclic integral of dq by t means? Cyclic integral of dq by t represents the total change in dq by t. Total change in this dq by t, right? And the total change in dq by t is coming out to be how much? Zero. Now, if you look back at the cycle, this is only possible if dq by t is a property, must be a property. Why? How? Because you see, it is only if it is a property of the system, then only, right, the total change can be zero, because the initial condition equal to final condition. Now, initial for a cycle. Now, for a cycle, if something is zero, right, the net change in the set parameter is zero, it must be a property. For example, say, let me set the temperature. Initial temperature was Ti, and finally, after the cycle, again it reaches the same point. Again, the final temperature is that. Now, what is the total change in temperature? Zero, right? If you say internal energy point 1 cannot be 2, right? There has to be one single internal energy. So even if you are performing the cycle and you are returning to the final state, the initial state equal to final state, then total change in internal energy is zero. Similarly, if the total change in dq by t is zero, what it means that this must be a property, right? And Clausius went on to name this property as entropy, and started researching on entropy. So entropy got researched more and more, and what was found that entropy is nothing else. It is a thermodynamic property of a system that describes the degree of molecular disorder or molecular randomness. Now, if you remember, in one of our earlier lectures, we spoke about sensible energy. We spoke about sensible energy. Sensible energy is the energy, right, because of the vibration of the molecules, right? It might be linear vibration, it might be rotational vibration, it might be spin, whatever it is, the vibration of the molecules. And this is directly related to what temperature. So the temperature increases, right, the sensible energy increases, the vibration increases. So similarly, entropy is also a measure of the vibration. What is the molecular disorder, molecular randomness, the vibration of the molecules? You can understand it this way. Okay? And it emerges, as you can see, it emerges as a consequence of second law of thermodynamics and Clausius inequality. Now, people were starting to understand what exactly is entropy. They were finding it difficult, like you are doing right now. So, a lot of studies were done, and people kept on asking Clausius, now, can you explain it even further? Can you explain it even further? Can you explain it even further? Then he told that, okay, let us try to understand the concept of entropy even more. He said, for any process, for any process. Now, process does not mean a cycle. For a cycle, total change in entropy is zero. But for any process, there can be some amount of change in entropy. So, what is the total change in entropy for a process? He said the total change in entropy for a process, that is S2 minus S1. So if you want to draw it in any diagram, right? Let me say a system moves from point 1 to point 2, right? It undergoes a process from point 1 to point 2. So what I can say that the total change in entropy delta S, that is S2 minus S1, can be given as integration of dq by t, right, from 1 to 2 plus entropy generation. Acha? Then the scientist started asking Clausius, what do you mean by this? Can you explain it even more? He said, whenever this process is taking place, whenever the system is moving from 1 to 2, entropy changes because of two things. First is the heat transfer, that is dq. Whenever you are transferring some heat, what happens is that, suppose there is a system and you are adding heat to the system, what will happen to the molecular randomness? The molecular randomness, the vibrations will increase, isn't it? So does the energy, so does the entropy. So whenever you are transferring heat into the system, the entropy of the system increases. Similarly, what will happen? Imagine if the system is rejecting heat. If the system is rejecting heat, it is losing energy. And as it loses energy, what is going to happen to the molecular randomness? The vibration of the molecules, it will decrease. So it means whenever heat is transferred out, the entropy decreases of the system decreases, and whenever heat is being supplied, entropy of the system increases. So there is this change in entropy associated with heat, and this is what this first term is representing. That total change in entropy is basically given by total heat transfer divided by the temperature at which heat is being transferred. Then he went on to say, right, this is the entropy change because of, or I can say delta S, because of heat transfer. Then he went on to say that at the same time, there will also be some entropy generated in the process. So the people started asking, why? Because of irreversibility. Now let us take the example of friction, because it is very easy to understand with friction. Now, whenever a process is taking place, if there is friction, be it a piston cylinder or be it any other moving parts, or just it is fluid friction, whatever it is, right? Because of friction, what is going to happen? Some amount of energy, the kinetic energy, right, it is getting converted into what? Heat, isn't it? So once the kinetic energy is getting converted into heat, what will happen because of that heat? Again, the molecular randomness will increase, isn't it? So whenever there is any irreversibility, what will happen? Entropy will generate. This is because of delta S, because of irreversibilities. They said, okay, so this is the thing, that whenever a process is not reversible, means there are some irreversibilities, some amount of entropy is generated. And you can now understand why it is known as irreversible. Now, if the entropy is getting generated because of irreversibilities, no matter what you do, you cannot just reverse it back to its completely original state. And that is why the processes reversible and irreversible are there. So if the entropy generation is zero, we can say the process is reversible. If the entropy generation is not zero, the process becomes irreversible. The scientist said, can you explain this for a cycle? He said, okay, so in a cycle, there will be 3 to 5 processes. Let us say there are 4 processes. Now, whenever I want to find out the change in entropy, what is the total change in entropy, right? S2 minus S1 for a cyclic process, right? So let me say total change in entropy is cyclic integral of delta S. That is the total for delta S. Cyclic integral of dq by t, right? And we'll see if entropy is generated or not. Yeah. For all the four processes separately. Right? Now, for a reversible cycle, we all know that delta S total change in entropy has always to be zero, because in a cycle, right, if entropy is a property, if you reach from the initial point to the again to final point and initial point are same, so the total change in entropy has to be zero, right? Okay. Now, if the all the processes are reversible, then entropy generation will be equal to zero, right? For reversible. Right? And for the equality to hold true, this will also be equal to zero. That is, cyclic integral of dq by t is equal to zero. And this will satisfy everything for a reversible cycle. Okay. Now, what if it is a irreversible cycle? Now, for irreversible cycle, we all know that total change in entropy, it is still a cycle, it has to be zero. Now, entropy change is going to be positive, right? Because there will be irreversibilities which will result in generation of entropy. And for that, what is needed is that cyclic integral of dq by t has to be negative, because only then negative plus positive can become equal to zero. And that is what is the meaning is this cycle is still possible, right? But will be reversible, will be irreversible. Some amount of entropy has been generated. Now, if you take the third case, right, delta S is greater than zero. When will delta S is positive? Delta S positive means this is also positive, this is also positive, right? This is simply, right, del q by t. If del q by t is positive, del q by t is positive, now entropy generation can never go below zero, right? It cannot be negative. So positive, it is either positive or zero, whatever it might be, this cycle is not possible. This cycle is not possible. Why? Because total change in entropy for the cycle is coming out to be positive, which is not possible. I hope you understood the concept of entropy, right? Entropy generation, what is reversible and irreversible process in the minimum time required. Now let us try to understand what will be the entropy change of an universe. Now see, universe is considered to be what? It is considered to be an isolated system, right? Because neither mass nor energy can go out of the universe. Where will it go, right? Universe is everything, right? Isolated system. Right? So whatever process is happening inside this universe, right, be it reversible, irreversible. If it is reversible, so entropy generation is going to be what? Zero. If it is irreversible, so entropy generation is not going to be zero. Right? So in an universe, if you see, you will not find many of the reversible processes. Why? Because reversible are ideal processes which are not basically achieved. And even if you get it, right, most of the processes will be irreversible in nature, means entropy will be generated. So what is happening to the universe? If you see universe as a whole, the entropy of the universe is constantly increasing. The energy of the universe is constantly increasing. Having said that, let us try to find out how to calculate entropy. Now, in calculation of entropy, this tedious equation helps us. Now, what are these tedious equations? Now, we all know that delta S, the change in entropy can be given by dq by t, right? So what it means that this implies dq, I can say delta S or let me say T delta S, right? dq is equal to T delta S or TdS. TdS is nothing else but dq. Right? Now, if I take, now we know that Q is equal to what? Heat transfer. By first law of thermodynamics, you can say it is the total change in internal energy, right? dq, let me say total heat transfer is equal to total change in internal energy plus PdV, right? So what it means that TdS is equal to du plus P. I am writing Vd. I should write this PdV. Right? So PdV. So this is our first TdS equation. This is one of the equation which helps us, which is relating with internal energy. Right? We have one more TdS equation. Now we all know H is equal to U plus PV. Now if you differentiate H, we will have dH is equal to du plus, once we will differentiate V, so it becomes PdV. Then we are going to differentiate P, keeping V constant, so it becomes VdP. Now du plus PdV, we already have seen that this is nothing else but TdS. So dH becomes is equal to TdS plus VdP. So I can write again TdS is equal to dH minus VdP. So the second equation, it helps us. It is a relationship between what? Enthalpy and TdS. Now these are the two equations, general equations, which are valid for all processes. These are valid for all processes. Valid for all processes. And this equation helps us in finding out, in calculating the entropy change for a process. Now, if you want to calculate entropy change, now I'm going to give you a very, very simple way of finding out the entropy change. Okay? Please look at this very carefully. The first question that you are going to ask, is there any temperature change? Is the temperature changing? If the temperature is not changing, simply delta S is going to be change, or I can write ds better, right? Small amount of entropy change, right? I can simply say ds is equal to dq by t. Means simply if the temperature is not changing, whatever is the heat transfer divided by temperature, because the temperature is constant, and you will get the change in entropy. Now, what if the temperature is changing? Yes. What if the temperature is changing? Then you are going to ask again one question: is the system, right? Is the matter inside the system, is it a solid? Is it a liquid? Or is it a gas? Now, if it is solid or liquid, we all know that ds is equal to dq by t, right? dq by t. So ds can be written as, dq can be written as mc dt by t. Right? Why? Because for solid and liquid, we know that there is only one heat capacity, and simply you can integrate this and you can actually find out. For solid and liquid, this is how you are going to find out dt. Now, if it is a gas, again you are going to ask two questions: is it a real gas or is it an ideal gas? Ideal gas is a gas which follows the ideal gas equation. Now, if it is an ideal gas, by integrating, we know there are two values of C here, right? Cp and Cv, right? By integrating TdS equation, we have two equation, S2 minus S1. It can be written as Cv ln T2 by T1 minus, plus R ln V2 by V1. Or in terms of Cp, you can write it S2 minus S1, that is delta S is equal to Cp ln T2 by T1, the first term remains same, T2 by T1, temperature is changing, right, from T1 to T2 in a process. minus R ln V2 by V1. So this is how, oh sorry, not V2 by V1, here it is going to be P2 by P1 in the second equation, ln P2 by P1. So this is how we are going to find out the change in entropy, whatever the process might be. Now, what if it is a real gas? A real gas, the equations will be provided, the relation will be provided, right? Or what you can do, we can use the TdS equation. Now, all these are calculated from the TdS equation itself. I'm not showing you all derivation, right? But these equations are from the TdS equation itself. Now, if you understand this, you'll be able to calculate entropy for any process you want. Now, let us see how to draw a TS diagram. So, in TS diagram, in the y-axis we represent temperature, and on the x-axis we represent entropy. Let me say the system is at point 1, right? And you are adding heat. If you are adding heat, I'll move the point 1 a little bit ahead so that I can show both heat addition and heat rejection to you. So if you are adding heat, if you're at point 1, if you're adding heat, this is how you'll go. On 1 to 2. Why? Because you are adding heat, the temperature increases, so does the entropy. Right? At the same time, if you're rejecting heat, this is where it will go. This is the first one is heat addition, and second one is heat rejection. Now, it also depends on the processes. This definitely what path it is going to follow. Is it an isothermal? Is it a if it is isothermal, definitely what will happen, right? It is going to be a straight line, right? Because the temperature remains constant. But this is basically what I'm saying, how it will look like for heat addition or heat rejection. But the exact diagram, because there are different processes, be it constant pressure, be it constant volume, uh, isothermal, adiabatic, and say polytropic processes, all different processes. We will learn it in the next lecture, how to draw the TS diagram, PV diagram, and TS diagram both, right? But this is how you're going to draw a TS diagram basically. And let us try to understand what does this TS diagram represents. This is more important for us to understand. TS diagram, if you're taking TS diagram, and let me say the process happens between 1 to 2. So 1 to 2. So what is the area? Now we all know that ds is equal to dq by t. So I can write dq is equal to tds, right? And if I integrate dq, so I'm going to integrate tds also. So what is the meaning? 1 to 2. So what I can say is that total heat transfer in the process 1 to 2 is equal to integration from 1 to 2 of TdS. So this is integration of TdS is nothing else but the area under the curve. Area, let me write it properly. Area under curve. Right? So the area under the TdS diagram, what it is representing is basically the heat transfer. Right? So we have successfully understood the second law of thermodynamics. We'll be able to understand it even more once we do the entropy, the Carnot cycle, where we'll be utilizing all these things, right? And you also carry out but before understanding Carnot cycle, we have to understand all the all the different processes and their relationships, PVT relationships, and how to draw a PV diagram, TS diagram, which is in the chapter 6. So thank you all of you. I hope you liked this video. Please let me know if you liked anything. Let me know in the comments what is that you like and what are the things that can be improved so that I can be of more help to you guys. And that is all I would like to say. I'll keep on coming up with more resources, more videos, more notes, more question papers, everything. I'll just try to help you with. Thank you guys. Bye bye. Take care.